Let us begin. We're going to take a brief look at problem number 10 on page 149. This is a circumstance in which a child is sliding down the banister, another name for a handrail, right? So you can think of a hand railing as you travel down or upstairs. So if you've seen in movies, or maybe you've done this yourself, you can slide down those if the handrail is wide enough. So the father wants his child to not be able to slide as successfully and as quickly down the handrail or down the banisters as is depicted here. His child is 41.2 kilograms. The angle that the banister makes with the horizontal is 52.4 degrees. We'll say that's what theta is. And what he changes about this banister is he adds some tacky substance to it, in which now it has a coefficient of static friction of 0.72, as opposed to something that previously was smaller. We're asked to find, well, what is the magnitude of the static frictional force that opposes his son when he sits on the banister. This is our picture that we have here of what's happening. This is what we observe. These are the data points that we have, the information we have about this given picture, this circumstance. And then the frictional force, the magnitude of the static frictional force, is what we're asked to find. We can simplify this picture or put it in through a physics lens right here. That's what we have here. I simplified the description of the child that's sliding down the banister by just representing him with a box. Could have represented him with a dot just to make things simpler. And instead of drawing out the entire banister, all I did was draw something similar to some inclined plane that's inclined at 52.4 degrees above the horizontal. After doing so, I represented all of the different force vectors that are acting on our box, which is representing the child. We have the normal force because this box, this child, is in contact with the banister. So the surface exerts some force onto the child that's perpendicular to the surface. We, of course, have a child that has some mass of 41.2 kilograms. Because he has some mass and is in a gravitational field, then he has a weight. And then lastly, we have a frictional force that's in the opposite direction in which the child wishes to go, which is down the banister. So the static frictional force is oriented parallel to the surface and upwards along the banister. We split the weight into two components. We resolve it into the y component that is perpendicular to the surface and the x component of the weight, which is parallel to the surface. I zoomed in on this picture here on the right to where we have weight that is directly downwards. I put a dashed line here to represent the incline of the surface or the banister. And then weight in y, which is perpendicular to that incline. Weight in x, which is parallel to the surface. We tilt our axes so we can analyze this more simply. So we kind of turn our head 52.4 degrees to the left, and we turn and we see that we can treat now this dimension, this turn dimension, this perpendicular dimension to the inclined plane, that's now our y dimension, and the inclined plane itself, that line, is now the x dimension. All right, let's look back at what we're trying to find. We're trying to find what the magnitude of the static frictional force is. Well, our equation for static frictional force is whatever the normal force is times the coefficient of static friction. We're given the coefficient of static friction, so we know that already. We just need to find, well, what is the force that the surface exerts on the child? In other words, the normal force. We've done this before. We've resolved the components in the y dimension using Newton's second law, and we always find in these circumstances that the normal force is equal to weight in y because the child is not accelerating away from or into the banister. So these two forces must be equivalent to each other. If we look back at our picture here, we see that the normal force is directly opposing the weight in y. So those must be equal to each other. We do a little bit of trigonometry related to this larger picture here. We see that weight in y, which is adjacent to the angle theta, which is 52.4 degrees. Adjacent, we're going to use cosine. So mg cosine of theta is what the normal force is equal to. Put that back into my original equation for the static frictional force. Mg cosine theta, the normal force, times our coefficient of static friction, mu, gives us 180 newtons. Remember, we're given m 41.2 kilograms. We know g 9.8 meters per second squared, or 9.8 newtons per kilogram. Cosine of 52.4 degrees times the static friction coefficient, 0.72. We find that frictional force is 180 newtons directed upwards or up along the banister. Now, a related question, however, would be, well, is this enough friction to stop the child from sliding down the banister? The answer is no. There is a force that's trying to send him down the incline, and that would be weight in X. That's the X component of the weight or of gravity that's acting on the child, that's trying to pull him down along the incline. Down along the incline. That's this force vector here. How strong is that force vector? What's the magnitude of that force vector? It's mg sine of theta, right? If we go back to our vector triangle here, sine is opposite of the angle, right? So weight in X is the vector that is opposite our theta. So we're going to be using sine. Mg sine theta gives us what the magnitude of weight in X is. Mass, 41.2 kilograms, times our g constant, sine of 52.4 degrees. And we find that it's 320 newtons of force. That's the force of gravity that wants to pull the child along the incline. If we compare 180 newtons to 320 newtons, we see that despite the father's effort to increase the static frictional force to 0.72, that 180 newtons of force is not sufficient to overcome the force of gravity that's acting on his child. We see that the weight in X is stronger in magnitude than, or is greater in magnitude than the static frictional force. Therefore, the child will still be able to slide down the banister. All right, thank you.